Coal. The fuel that built the modern world. The fuel that's been slowly choking it ever since. Dirty, carbon-soaked, supposedly on its way out. So will someone please explain to me why Chinese scientists just figured out how to turn it directly into electricity, without burning a single gram of it? No fire, no smoke, no steam turbine, no combustion of any kind. Just coal going in and electricity coming out, with the only byproduct being a stream of pure CO2 so concentrated it can be captured, converted, and stored before it ever sees the atmosphere. The internet found this story in early May 2026 and completely lost its mind. Posts spreading in a dozen languages within 72 hours. And honestly, for once, the reaction made complete sense. Because if this works at scale, it does not just change how China powers itself. It changes the math on coal for every country on Earth that still depends on it. And right now, that is most of them. China's energy paradox. Here is what people do not understand about China's energy situation. In 2025 alone, China built 78 gigawatts of new coal power capacity. To put that number in context, that is more than the entire electricity generating capacity of the United Kingdom, added in a single calendar year. At the same time, China is the world's largest builder of solar panels, wind turbines, and battery storage. Both things are true simultaneously. And that is not a contradiction. That is a survival strategy for a country of 1.4 billion people that cannot afford blackouts. But there is a problem hiding underneath the surface of all of that coal. China's shallow coal reserves, the cheap, accessible deposits near the surface, are running out. What is left is buried more than a kilometer underground, expensive to mine, dangerous to extract, increasingly uneconomical to ship across a country that size. So the question Chinese researchers started asking was not, how do we burn coal more cleanly? That question had been asked for decades and produced nothing worth talking about. The question they started asking was entirely different. What if burning coal was the wrong approach from the beginning? Enter Xi Heping, academician at the Chinese Academy of Engineering, professor at Shenzhen University. And the man who decided the fundamental problem with coal was not the coal itself. It was what we had always done with it. But to understand why his team's answer is so significant, you first need to understand the wall every power plant on Earth has been running into for 200 years. So what if instead of burning coal, you just wired it directly to the grid? No fire, no steam, no turbines. And that's exactly what his team built. How the coal battery works. Every power plant you have ever seen works the same basic way. You burn something. The heat from that combustion creates steam. The steam spins a turbine. The turbine generates electricity. Simple in principle, catastrophically wasteful in practice. Here is the problem. Every single step in that chain loses energy. By the time electricity actually reaches your wall socket, you have already thrown away more than half the energy that was locked inside the original fuel. That is not a design flaw that engineers failed to solve. It is a fundamental law of physics called the Carnot limit. The Carnot limit says this: any engine that converts heat into mechanical motion is mathematically capped by thermodynamics. The best coal plants ever built hit around 45% efficiency. The other 55% just disappears as heat, forever, no matter how clever the engineering gets. You cannot engineer your way out of a law of physics. Xi Heping's team did not try to beat the Carnot limit. They removed it from the equation entirely. The technology they built is called the Zero Carbon Direct Coal Fuel Cell, the ZCDCFC. Think of it as a battery where coal is the fuel. And once you understand how it actually works, the efficiency numbers stop seeming impossible and start seeming inevitable. First, the coal gets pulverized into an ultrafine powder, particles smaller than 10 micrometers, thinner than a human hair. Then it gets dried and chemically cleaned to remove sulfur and ash. This matters because what happens next is extremely sensitive chemistry. That purified coal powder gets fed into the anode chamber of a fuel cell. On the other side is the cathode, where oxygen enters. Separating them is a ceramic membrane that conducts oxygen ions at high temperature. At somewhere between 600 and 900 degrees Celsius, the oxygen ions migrate through that membrane toward the carbon. And here is where the physics takes a completely different turn than every power plant ever built. When the oxygen ions meet the carbon atoms, there is no combustion, no fire, no heat burst. Instead, you get a direct electrochemical reaction. Carbon and oxygen combine, and the energy that releases does not escape as heat into the atmosphere. It flows out as electrons, as electricity, directly, without any intermediate step. Traditional coal plants, 33 to 45% efficiency. The ZCD-CFC theoretical ceiling, 90%. Real-world practical efficiency demonstrated in the lab, 55 to 60%. Even accounting for all the energy spent grinding, drying, and maintaining operating temperature. It is still the most efficient coal power technology ever demonstrated anywhere. But efficiency is only half of this story. The half that actually broke the internet is what happens to the carbon. Because there is no smokestack. There is just a pipe, with pure CO2 coming out of it. And the team already figured out 3 different things to do with that too. The zero carbon claim and the underground power plant. In a normal coal plant, the CO2 that comes out is mixed with nitrogen, steam, sulfur dioxide, and particulates. It is a mess. Separating usable CO2 from that mixture costs between $50 and $100 per ton, and that cost is one of the biggest reasons clean coal has been a punchline for 30 years rather than a real technology. In the ZCD-CFC, the anode is sealed. The carbon never touches open air, so the CO2 produced comes out already pure, already separated, already ready to use. The Shenzhen University team laid out 3 pathways for it. Convert the CO2 to syngas through a process called dry reforming. Syngas is a building block for synthetic fuels, plastics, and fertilizers. Your waste carbon becomes an industrial feedstock. Mineralize it. React it with mineral compounds to form solid sodium bicarbonate, chemically locked into a stable solid permanently. Inject it back underground into depleted coal seams, where it enhances recovery of natural gas, while keeping the carbon stored below the surface. In simple terms, the carbon becomes manageable because it was never allowed to mix with open air in the first place. In all 3 cases, the carbon never reaches the atmosphere. That is not a marketing claim. That is a closed loop built into the chemistry of the device itself. Now, here is the part that goes from impressive science to genuinely reality bending. The team's most ambitious proposal is not to build the fuel cells at the surface at all. It is to put them underground, right at the coal seam. Instead of mining the coal, transporting it across the country, and burning it in a massive industrial complex, you drill a borehole. You lower modular fuel cell stacks down to the coal deposit, 1 to 2 kilometers underground. You convert the coal into electricity right there where it sits, and the only thing that travels back up to the surface is a cable carrying electricity. The CO2 stays underground. The ash stays contained in the seam. The surface footprint is a few drilling pads, no coal trains, no ash ponds, no cooling towers, no visible industrial footprint at all. That is the proposal. An underground power plant with essentially no surface infrastructure, running on a coal seam that would otherwise be too deep and too expensive to mine. Now, before you start recalculating your entire mental model of how energy works, it's worth being honest about where this technology actually stands, because this is where the story gets more complicated and, in some ways, more interesting. Reality check. The chemistry is real. Electrochemical coal oxidation has been demonstrated in research labs since the early 2000s. The efficiency gains are real. Bypassing the Carnot limit through electrochemistry is not theoretical. It is proven physics. The pure CO2 capture is real. It is an inherent feature of the sealed cell design, not something added on top. What is not proven yet is everything that happens between a working laboratory cell and a commercial power plant. Long-term durability is an open question. Can ceramic cells of this type run for 10,000 hours or more without degrading? The honest answer right now is that researchers are working on it. Continuous coal feeding at scale is an engineering nightmare. Feeding a fine powder into a sealed high-temperature system without interruption, without blockages, without pressure fluctuations, is not a solved problem. The advanced ceramics and precision materials involved are expensive. Experts looking at the commercial pathway are realistic about the timeline, post-2045 at the earliest for meaningful scale deployment. And there is one more thing worth saying clearly. If the captured CO2 eventually gets converted to syngas, and that syngas gets burned somewhere down the line, you have delayed the emission, not eliminated it. The zero carbon claim depends entirely on what happens to the carbon after capture. The science gives you the option to close the loop. Whether that option gets taken depends on economics and policy. This is not clean coal in the sense that politicians used that phrase for 2 decades as a talking point to avoid real decisions. It is not a scam, but it is also not a switch you flip. It is a 20-year research and engineering project that just published a very significant paper. That distinction matters. Why this matters for the whole world. What also matters is what this technology could mean for the countries that need it most. Because this story is not really just about China. Coal currently generates about 35% of the world's electricity. It is not disappearing in a decade. Not in India, where coal provides more than 70% of electricity. Not in Southeast Asia, where energy demand is growing faster than any renewable build-out can currently match. Not in parts of Africa that are still trying to reach reliable electricity access at all. The argument against fast renewable transitions in developing nations has always come down to the same 2 things: reliability and cost. Solar and wind are intermittent. Battery storage is expensive. Coal is cheap, domestic, and works when the sun does not shine. That argument has been winning in a lot of places, and the climate consequences of it winning are real. If the ZCDCFC delivers on its promise, it changes that calculation. You get the reliability of coal, efficiency that beats the best natural gas plants, and emissions that can be captured at the source. For countries sitting on massive domestic coal reserves, this is not just an energy story. It is an economic argument for a different kind of transition. One that does not require abandoning your most abundant resource before you have a viable replacement. And then, there is the geopolitical layer, which is worth sitting with for a moment. China already controls roughly 80% of the global solar panel supply chain. They dominate battery manufacturing. They lead in wind turbine production. If ZCDCFC technology matures and scales, they would not just lead the clean energy transition, they would lead the fossil fuel transition too. They would become the country that sells the technology, allowing coal-dependent nations to decarbonize while keeping their domestic energy resources. That is not an energy strategy. That is a foreign policy strategy. And it is being built right now in a laboratory at Shenzhen University, inside a sealed ceramic cell the size of a research bench. The team is targeting a commercial pilot phase sometime after 2045. In the long history of energy transitions, that is not a distant abstraction. Steam engines took a century to be replaced. Nuclear power was conceived in the 1930s and still only generates about 10% of global electricity today. Energy transitions move in decades, and the decisions that shape them get made in laboratories long before any investor writes a check or any government signs a mandate. The ZCDCFC is not the end of coal. It might be coal's second chapter, as something that looks a lot less like a fossil fuel and a lot more like an electrochemical feedstock, something you feed into a device underground and pull electricity out of while the carbon stays locked below where it came from. If that sounds strange, keep this in mind. The physics is not broken. The chemistry is not speculative. What is changing is the assumption we always carried that coal had to be burned to be useful. That assumption is 200 years old, and a research team in Shenzhen just quietly finished writing the argument against it. If you want to stay ahead of the technology shifts that matter before they go mainstream, subscribe.